Good day, viewers. So welcome to another edition of NAMSSN tutorial. So this is a Laurent series, Laurent and Taylor series. So in real analysis, we are familiar with Taylor and Maclaurin series. Anytime we are given a function, let's say f of x, let's say f of x is equals to cos x, and then we are asked to expand this function using Taylor series. So we know that if I want to expand f of x, I will need f of, let's say I want to expand at x equals to a, for example. So I would say f of x equals to f of a plus first derivative of this function at a, f prime of a plus f prime prime of a divided by 2 factorial plus f prime 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 divided by 3 factorial of a. So and on like that. So we are familiar with this expansion. So here now we are taking Taylor and Laurent series to complex variables. So how do we expand complex variables? By using Taylor and Laurent series. So the slight difference between real and complex is that the function we want to expand, it has to be analytic inside a closed loop. Okay. Now let's take a theorem and then we'll start from here. The theorem states that let f of z be analytic. Let f of z be analytic in the disk. Let's say inside the disk, let's call the disk C, such that absolute value of z minus z naught is less than r. And let's say let z be a point. Let z be a point in the disk. Choosing C to be positively oriented, such that absolute value of z minus z naught is less than p less than r. Therefore, that function z, it can be expressed as summation n start from 0 to infinity of ck z minus z naught all raised to power of k. So this is the theorem. So let f of z be analytic inside the disk C. We know what analytic, when the function is analytic, it means that the function is differentiable at a particular point z naught and is also differentiable at the neighborhood of that point. So such that we have z minus z naught less than r. Now let's prove the theorem. Now suppose we have a closed disk like this, and then we take a point, we take a loop inside that disk. Let's say, okay, this is disk of is a circle, and then from center to circumference is the radius of the circle. And I take, let's say, I take another loop inside this disk. Let's say I pick a loop like this. I pick a loop within that region. What that theorem is talking about is that the meaning of this z minus z naught less than p less than r. This is z, and then let's say this region, let's call it z naught, and then let's say from this center to the circumference of this one is let's call it p. You observe that if I'm moving from here to here, if I'm moving from here to here, and if I'm moving from here to here, this one is definitely greater than this. So it means that if the distance from z to z naught, the distance from z to z naught is what? Is greater than distance from this to this circumference, greater than p, and that is less than what? this radius is less than r. That is, if I'm going from here, this is r, this is the radius of the circle. From here to here is the radius. So if you are moving from z to z naught, the distance from here to here is definitely bigger than the distance from this region to this region. So z minus z naught is less than p, and then this p is definitely less than r. Look at it, the distance from here to here and the distance from here to here, definitely this one is longer than this. So what do we want to use it to do? Now let's take any arbitrary point. Let's say point s inside this disk. So let's take an arbitrary point. Let's take an arbitrary point s inside the disk. In our previous video, we are using loop for Kochi. So here we are using disk. So you observe that if I have 1 over s minus z, for example, if I say 1 over s minus z, I can actually manipulate my way by saying this is like 1 over s minus z naught plus z naught minus z. It's the same thing. So 1 over s minus z is 1 over s minus z naught plus z minus z naught. Okay, so before I go further, there are some in our previous year, maybe year 1 or secondary school, there are some expansion that we really need. So let me just put that one somewhere. Let's put it here. Where can I put it? Useful expansion, because I will be making reference to all those expansion as the video goes on. Just put down at the back of the notes useful expansion. Useful expansion, or let's say useful series, series. Anytime we see 1 minus z, or 1 over 1 minus z, or 1 minus x, it's like 1 plus z plus z square plus z cube plus on and on like that. That is a summation z raised to power n, where z starts from 0 to n. So this is 1. And then if we are having 1 over 1 plus z, so this one will be alternating. It will be 1 minus z plus z square minus z cube and on like that. That one will be summation minus 1 raised to power n z raised to power n, where z starts from 0 to infinity. That's another expansion that we need. Anytime we are dealing with trig function like sin z, sin z is an odd function. That's z minus z raised to power 3 over 3 factorial plus z raised to power 5 over 5 factorial and not like that. And also cos z, cos z, cos z, that one is even function. It will start from z squared, or no, it starts from 1 plus z square over 2 factorial minus z raised to power 4 over 4 factorial plus z raised to power 6 over 6 factorial and so on like that. And then e raised to power z, let me put that one here as well. E raised to power z, e raised to power z is 1 plus z square over 2 factorial, z raised to power 3 over 3 factorial, z raised to power 4 over 4 factorial and none like that. So these are the useful series that we are going to be making reference to. Now, from here, when I take an arbitrary point x inside this disk, so 1 over s minus z is just like saying, okay, if I have z naught and if I add and subtract z naught from both sides, I'll still have 1 over s minus z. So which is 1 over, if I separate them into 2, this is like s minus z naught minus z minus z naught. I've not changed anything. This is minus z naught, this is minus z, this is minus minus, that's plus z naught. Then if I try to factorize s minus z naught, don't forget, this is what I'm doing. I'm taking 1 over s minus z inside this disk. So 1 over s minus z is equals to, if I factorize this one, if I factorize s minus z naught, that will be 1 over s minus z naught into brackets. If I factorize this, I'm going to have 1 minus z naught. I have to divide by s minus z naught. So from there now, if I raise this one up, if I raise the expansion up, so we are going to have 1 over s minus z naught into, or don't forget from indices, if you have 1 over x raised to power a, it will turn to x raised to power minus a. So if I bring this one up, it will turn to 1 minus z naught all over s minus z naught, all raised to power minus 1, all raised to power minus 1. And if you can recall from this my first useful series, anytime we are having 1 over 1 minus something, you know, this one now, if I write it in another form, I can say this is 1 minus z raised to power minus 1. So 1 minus z raised to power minus 1. Here is 1 minus a function raised to power minus 1. So it will be 1 over s minus z naught into bracket 1. This is it. 1 plus the function plus the square of it plus the cube of it. So this is 1 plus z minus z naught divided by s minus z naught plus z minus z naught divided by s minus z naught, all squared, all cube, and on like that. That is what? 1 over s minus z. So if I take the summation of all this, so this will be 1 over s minus z naught into bracket 1 plus z minus z naught square. We can generalize it as this is summation z minus z naught divided by s minus z naught, all raised to power what? Let's say all raised to power k, where k starts from where? K starts from 0, end at infinity. So is equals to, this is where we are coming from, 1 over s minus z. If I now open the brackets here now, if I open the brackets with 1 over s minus z naught, this will be summation z minus z naught all raised to power k divided by s minus z naught times s minus z naught raised to power k. It will be s minus z naught all raised to power k plus 1. So we are getting there. That will be s minus z naught all raised to power k plus 1. So I'll clean this. So we are having 1 over s minus z equals to summation k starts from 0 to infinity of z minus z naught all raised to power k divided by s minus z raised to power k plus 1. So from here now, don't forget we are coming from a closed disk like this, a circle. So if we integrate both sides, if we integrate both sides around a circle, so around a circle, that is, I'm integrating 1 over s minus z or ds around a circle like this is equals to integral of c summation k starts from 0 to infinity of z minus z naught all raised to power k divided by s minus z naught raised to power k plus 1. And then we multiply by f of s. Let's multiply by f of s. If I multiply both sides by f of s, I'm going to have f of s or f of s integrate with respect to s, both sides. So from here now, I can actually take this summation out. This will be summation k starts from 0 to infinity integral around a closed disk. So in some textbook, they can say they are integrating from 0 to 2 pi. If you are moving from 0 to 2 pi, it means that you are moving around a complete circle. So the same thing as using this sign, integral of c. So this will be integral of c f of s divided by s minus z ds is equals to summation k start from 0 of f of s times z minus z naught raised to power k divided by s minus z naught all raised to power k plus 1 ds. And then if we represent everything here by f of z, so let all this stuff, this left hand side, let this integral, let's call it a function z, and then this part, this part, so everything here, let's call it ck. Let's integral of c of f of s divided by s minus z naught all raised power k plus 1. Let's call it ck or ak or whatever I want to call it. So let's call it ck. What do we have now? So everything here now, we tag it as f of z. So f of z equals to what? This summation will still be there. Summation k start from 0 to infinity of this integral, everything here like this. We call it ck. And what do we have left? Z minus z naught all raised power k. That's Taylor series. So f of z equals to summation ck z minus z naught all raised power k. So this is Taylor series. This is the first Taylor series. So from here now, if I want to generalize or I want to get the nth term, so if I differentiate both sides, f prime of z, so well, this is actually Taylor series that we are looking for, but I want to generate the nth term. So if I differentiate this part now partially with respect to z, you know, it will be summation k start from 0 to infinity. If I differentiate z minus z naught raised to power k, don't forget chain rule. This k will multiply like this. We are going to have k times ck z minus z naught raised to power, we subtract 1 from this one, k minus 1. And if I differentiate again, f prime prime of z, f prime, yeah, the meaning of that 1 over 2 pi I, it means that we are moving around a circle. I've said is that you can use 1 over 2 pi I, that's when we are moving around the circle, or you can use c like this. The meaning of this c means we are moving around a complete circle. So f prime prime of z, so f prime prime of z is multiply this one by k minus 1 again. That's summation k start from 0 to infinity of k times this, k minus 1 ck z minus z naught raised to power k minus 2. And if we differentiate again, take the third derivative with respect to z, so that will be summation k start from 0 to infinity k times k minus 1 times k minus 2 of ck z minus z naught all raised power k minus 3. I think with that we've gotten a pattern: k minus 1, k minus 2. So the nth derivative, so fn of z, it will just be summation, this will be k factorial, where k starts from 0 to infinity, k factorial of ck z minus z naught raised to power k minus n. So this is the nth derivative of this Taylor series. And if we continue, say that let k equals to n, if I take k to be n now, when k is equals to n, when k equals to n, so this formula is too bulky, I want to shrink it. So if k equals to n, it means that this side is n, right? So we are going to have z minus z naught raised to power n minus n, and n minus n is 1. Sorry, n minus n is 0. Anything raised to power 0 here will be 1. So if k equals to n, so we are going to have the nth derivative of z. It will now be summation, this will be n factorial cn. N starts from 0 to infinity. And what is the meaning of n factorial? Summation of n factorial. That's n, n minus 1, n minus 2, n minus 3. So this is another way of generalizing Taylor series. So basically Taylor series is that whenever we are asked to expand a complex variable at a particular point z naught, we first put that z naught in that function, and then we differentiate, we continue to be differentiating until we generate the nth term. So let's take for example, so let's obtain the Taylor series, of f of z equals to 1 over z at z equals to 2. F of z equals to 1 over z at z equals to 2. So we want to get the Taylor series of this function 1 over z at z equals to 2, it means that our z naught is equals to 2. So we are expanding around z equals to 2. F of z equals to 1 over z. So what do? We first substitute these two here, we get f of 2. That's f of z naught. And then we continue differentiating like 3 or 4 times, then we get nth derivative. So our knowledge of differentiation here is very, very in depth. So we need what is it called? Nth derivative. So that is basically Taylor series. So Laurent series is just like the advanced version of this Taylor series. So let's do this. Let's expand 1 over z at z equals to 2. Now I want to expand f of z equals to 1 over z at z equals to 2. Now we need f of 2, f of these two, f of 2. That's 1 over 2. Fine. Then we start differentiating from here now. So what is f prime of z? If I differentiate 1 over z, that's what? Minus 1 over z square. We are differentiating z raised by minus 1. That will be minus z minus 2. And then what is f prime of 2? Because we are expanding at z equals to 2. That will be minus 1 over 2 squared. That was minus 1 over 4. Then what is the second derivative of z? If I differentiate minus 1 over z square, this is what I want to differentiate now. This will be 2z minus 3. That will be 2 over z raised by 3. And what is f prime prime of 2? Yeah, we are putting 2. That was 2 over 8. That was 1 over 4 as well. Then the third derivative of z. The third derivative of z is when I differentiate 2 over z cube again. This will be minus 6 z raised by minus 4. That will be minus 6 over z4. At z equals to 2, that's minus 6 over 2 raised by 4. Minus 6 over 16. That's 3 over 8. That's my f prime prime of 2, or minus 3 over 8. Then if I take one more, what is the fourth derivative of z now? If I differentiate this function again, it means I want to differentiate this. That's minus 6 times minus 4. That's minus 20. That's 24. This is 24 over z raised power 5. And f4 of 2. That's 24 over 2 raised to power 5. 24 over 32. So 24 over 32, that's 24 over 32. 8 here 3, 8 here 4. So that's 3 over 4. So if I stop there, from there now I can generate the nth derivative. How do I get the nth derivative? Just look at the trend. The trend fn of z. If f of z is 1 over z, f prime of z is minus 1 over z, f prime prime is 2. The third one is minus. It means that the series are what? They are alternating. So I'll first have minus 1 raised power n. Then this is 1. This is 2. This is 6. 2 is 2 factorial. 6 is 3 factorial. 24 is I think 4 factorial. So this will be n factorial all over the denominator. This is z raised power 1, z raised power 2, z raised power 3, z raised power 4, z raised power 5. That's z raised power n. So this is our nth derivative. Why minus 1 raised power n is because our derivative are what? They are alternating from minus to plus to minus to plus. If you differentiate this one again, you get minus. But if you differentiate 24z minus 4, if you differentiate 24z minus 4, you get minus something. So that is why this stuff is there. So if I now want to write my Taylor series out, if I want to write the Taylor series, so it will just be f of z. My f of z equals to the first one. The first one is 1 over 2 plus z minus z naught. Our z minus z naught, that's plus z minus z naught. Our z naught is 2. That's z minus 2. But let me write the formula first. Let me write the formula. So f of z will be f of z naught plus f prime of z naught times z minus z naught plus f prime prime of z naught times z, this is z naught, z base 0, sorry, z minus z naught all squared over 2 factorial and on like that. So then That's really jargon. This one is even better. So f of z equals to f of z naught is 1 over 2. The first derivative is minus 1 over 4 times z minus 2. The second one is the second one is 1 over 4 as well, but that one is plus. Plus 1 over 4 times z minus 2 all square divided by 2 factorial. Plus the third one, the third derivative is minus 3 over 8. So this one will be minus 3 over 8 z minus 2 raised to power 3 divided by 3 factorial plus the fourth one is 3 over 4. 3 over 4 z minus 2 raised to power 4 divided by 4 factorial and on like that. So our f of z will now be 1 over 2 minus 1 over 4 into z minus 2. 2 factorial times 4, that's 8. Plus 1 over 8 z minus 2 all squared. 3 over 3 factorial. This is 3 times 2. This one cancels, that's 16. Right? So this is 16. So this is minus 1 over 16 z minus 2 raised to power 3. And this one will be what? 4 factorial is 4 times 3 times 2. 3 will go. 4 times 4 times 2. That's 32. So plus 32, that's 1 over 32, sorry. 1 over 32 z minus 2 all raised to power 4. And so on like that. So that is how to generate Taylor series. So it's very easy. Just take the function. If they ask us to obtain the Taylor series at z equals to a particular point, we are going to be differentiating the function and then we are putting that particular value. So the relationship between Taylor and Maclaurin series is that if they ask us to expand this function now at z equals to 0, so it has turned to Maclaurin series like that. This one will be z minus 0, z minus 0, that z minus 0. But if we are expanding at a particular z greater than 0, so that's Taylor series. Take the function, differentiate it, put the value, differentiate it again, and then generate the nth term. So that is a Taylor series. So let's solve one more examples on Taylor series before I move to Laurent series. So that one is a bit difficult than the other one. So let's expand using Taylor series. 2 over z minus 1 z minus 2 at z equals to 3. This is 2. So using Taylor series, once you expand this complex variable f of z equals to 2 divided by z minus 1 and z minus 2 at z equals to 3. What do we need? We need f of 3. So what is f of 3? Put 3 here, put 3 here. This will be 3, 3. 3 minus 1, 2, 3 minus 2, 1. 3 times 1, 3. That's 2 over 3. Sorry. 3 minus 1, 2. 3 minus 2, 1. That's 2 over 2. That's 1. F of 3 is 1. Yeah, then we differentiate f prime of z. So how do I differentiate 2 over z minus 1, z minus 2? Well, before I differentiate, let's expand the denominator first. So f of z will be 2 over, if you expand this, that will be z squared minus 3z plus 2. Then how do we differentiate this? Quotient, what is it called? Chain rule. You are differentiating 2 times z squared minus 3z plus 2. Then what do we do? This is raised to power minus 1, and then 2 multiply minus 1, you differentiate this. That's 2z minus 3, z squared minus 3z plus 2 raised to power minus 2. Or that's this is minus 2 times 2z minus 3 over z squared minus 3z plus 2. Now what that's this is f prime of z. So what is f prime at this 3? F prime of 3 is what? Put 3 here. Already, if I put 3 here, I'll get 3 minus 1, 3 minus 2. That's 2. Everything here is 2. If you put 3 here, 2 times 3, 6. 6 minus 3, 3. 3 times minus 2, minus 6. So we are going to have minus 6 over 2. That's minus 3. Then we take the second derivative of z. So if you want to differentiate this stuff again now, you have to use what is it called? Product rule, because we already have two functions z in two sides. So how do you use product rule? This will be minus 2. Product rule is v du plus u dv, right? So v, this is our u, this is v. Forget about this constant first. So v, z square minus 3z plus 2 raised to minus 2, differentiate 2z minus 2, that's 2. Multiply by this, or multiply by this, that's minus 2. This is v du plus u now. U is this, minus 2 times 2z minus 3. Differentiate this. If you want to differentiate this, that's another chain rule on its own. These two also multiplied, and then you differentiate z square minus 3z plus 2. That's 2z minus 3 raised to power times z square minus 3z plus 2 raised to power minus 3. So it is quite complicated. Just substitute the value. Well, let's write it out. This is a minus 4. This will be minus 4 over z square minus 3z plus 2 all squared. Because if I raise this one down, that's all squared. And then this is what is this? Differentiate this, write this. So this is 2z minus 3. So minus 2 times minus 2, that's plus 4. This will be plus 4, and this. That's 2z minus 3 all squared all over z squared minus 3z plus 2 raised to power 3. Now, the second derivative at z equals to 3 now. At z equals to 3. If you put 3 here, I already know that this is what they're actually repeating. So if I put 3 here now, this is like 3 minus 1, 3 minus 2, 2. This will be minus 4 over 2 plus, put 3, put 3. So if I put 3 here, definitely, oh, this one is squared. This is squared. This is squared. This is 2 squared. Everything will carry square. So this is 4, 2 times 3, 6 minus 3, 3. 3 squared divided by, well, this one depends on your knowledge of computation. It's not hard. So if you put 3 here, 3 squared, 3 minus 1, 3 minus 2. 3 minus 1 is 2. 3 minus 2 is 1. So 2 times 1, 2. This is 2 raised to power 3. And then this one is minus 1 like this. This is 8. 4 over 8 is 1 over 2. This will be plus 9 over 2. So minus 1 plus 9 over 2. That's 7 over 2. So I'll stop there. The derivative is quite complicated. So the f of z will now be what? F of 3 plus f prime of 3 at z minus 3 plus f prime prime of 3 at z minus 3 all squared divided by 2 factorial, and all like that. So we go on like that. So this function now, 2 divided by z minus 1, z minus 2. Another way of doing it, if you don't want it to be complicated, is that resolve this one into partial fraction. If you resolve it into partial fraction, you have two separate fractions. Then you will be differentiating them one by one. So what I'm saying is that you are having 2 over z minus 1, z minus 2. If you don't want to go into this long process, resolve this one into partial fraction. So if you resolve it into partial fraction, let's assume you get 1 over z minus 1 minus 2 over z minus 2, for example. These are your functions z. Then you put z equals to 3. Put z equals to 3. You differentiate one by one. If you are differentiating this one, they will be easier than this. So if you know how to use partial fraction and then know how to use this one. But I guess this one is faster, because you first go into process of partial fraction before you come to this end. So whichever way you feel you understand, you can do it like that. So f of 3 is 1. F of 3 equals to 1. F prime